All right, welcome to Module 3. Now in Module 2 I touched on algorithms, and we also talked about different kinds of collections, how we group data together. Now, in a way, we could deal with Module 3 dealing with the default linear structure in Python, which is a list. But I'm not going to in this class because I want you to have an understanding of beyond just a list. We're going to deal with the sequential structure that we can get from the NumPy, N-U-M-P-Y, library. We can import NumPy, and in NumPy is a class that's been created, we can use it, that is an array data type. So by default, Python doesn't come with an array, but somebody created one. I'm glad they did. It's technically built off of the C programming language, but we can use it in Python. So we have an array data type available to us in Python. And we'll talk more and more about that in this module and subsequent modules. So in Module 3, we're going to deal with three things essentially. We're going to deal with arrays, that's the data type we're going to use, but we're going to be searching arrays, sorting arrays, and looking at the complexity analysis of these functions that we have available to us to search and sort an array. There's more than one way to search an array. So if I pull up, here's the overview as it exists right now as I'm recording this lecture. I've got some pseudocode here for the bubble sort algorithm. I've got a linear search algorithm, a binary search algorithm, a linear search compared to a binary search. And then I've got some different types of sort algorithms available to us. Now, let's start out by talking about the difference between searching and sorting. Now, let's assume I have an array, and that array has 5 values in it. The numbers 1, 2, 3, 4, and 5, in that order. How difficult is it for me to find or search that array for the highest value? If it's in order, and that example I just provided, the numbers 1 through 5, is in sequential order, ascending order, it's growing, any subsequent value in that array, so index I we would say would be the first value, any I plus 1, for any given value of I plus 1 is greater than I. That's an ascending sorted array. Let's say the first value was 5 and it decreased to 1. The index for the first value is 0. We know that for every I, as I increase I, for any value of I plus 1 is less than I. Now that's up to length minus 1, because we can't compare the last value with nothing. So for each item in there, if we compare it to the next one, and it is smaller, we know that that's a descending sort. If we can rely on the fact that everyone in an array, every item in there, the subsequent value is larger than the preceding one, that's sorted ascending. Now, things that are organized are far more easy to deal with. So a collection that is sorted, and we talked about this in the last module, a collection that's sorted, man, it's so much more efficient to be able to do things. Let's assume that that algorithm or that array was not sorted, and I want to find the largest value. Now I have to go through and compare every item to find the largest one. If it's sorted, I just go to the end. If it's sorted ascending, that's going to be index n minus 1, n being the length of the array. If it's sorted descending, I know the first value is the largest one. Arrays are something that allow us to randomly access any index in that structure. It is a sequential structure. It's stored in memory sequentially. Lists are not stored in memory sequentially. They're stored, I don't want to use the word pointers because Python really doesn't have pointers, but it's like a pointer. What we store in a list is the address of where the value is stored, and it's not sequentially in memory. In an array, we store things sequentially in memory. And I often use an analogy of a storage center that has many long buildings with units right next to each other. We'll say 10 units per building. Building A has units 0 through 9. Building B has units 0 through 9. And if I want to reserve 10 units, the only way I can do it is to get an entire building. That's how arrays work. If I run out of room in my array, I need to find space that is sequential that can accommodate how big the array is that I'm going to need. By default, the rule of thumb, if we're talking about small arrays, if you want to make your array bigger, you just double it. If you didn't have enough room to start with, double it. Save twice that much space in memory, and you should be fine. Now, if we're talking about really, really big structures, you're not going to double it. You know, if I have an array that has 5 trillion values in it, I'm not going to double that array and take up that much RAM from the system. So I need to think about space complexity and not just time complexity. Space complexity is how much RAM am I using at any given point. Time complexity is how long does it take the processor to do what it is we're going to do. Now, when I think about how long does it take the processor to do it, that's applied to a specific system. We're not digging down into that level of time complexity. We're just going to say on any processor, this is going to take n squared time complexity. Now, if the one processor is faster than the other, one's going to perform that task faster. So let's look at a search algorithm, a linear search algorithm. So I have a linear array. Here's a linear array. The length of this array is 9. The index of the last position is the length minus 1. These values are stored sequentially in memory. And when I say, I'll leave what I was about to say till the next module. We'll talk in the next module about logical space and actual physical space. So we'll just say that this array has 9 values in it that our function can access. And if I want to search for the value 20, assuming it only exists once, I'm going to look in the first position, see if it's there. If it's not, I go look in the next one, see if it's there. If it's not, I go to the next one. Now, if it is in any of these positions, then I'm done at that point, because I know it only exists once. If it exists more than once, we'll talk about that in a little bit, but essentially in our algorithm, we're going to read, do a comparison. If we find it, we'll break out. Else, we'll compare the next one. And as we compare the next one, the value of I, or our index, will grow by 1. And we compare it to I plus 1. No, on this one we're not doing a comparison. We're comparing it to a given value. So the given value is 20. Is I equivalent to 20? No. Increase the value of I. Is it 20? No. Increase the value of I. Is it 20? Nope. And we're going to go. And when the value of I is equivalent to 6, we found a match. And we're done. How many times did we go through this cycle? And this is a cycle. It's a loop. It's a for loop. And each time we compare what we have in that index with our given value. So in this instance, we went 7 times. We did one comparison here, another one, another one, another one, another one, another one. 7 comparisons that we did. And then we broke out. Now, our time complexity on this. Let's talk about that. We should at this point be okay with the concept of walking through this to find a specific value. What is the best case scenario when it comes to time complexity? 1. I looked for 20 and I found it in the first one. What is worst case scenario on this? 9. I had to go all the way down to the end. I compared 9 times. Now, if the length of this array is 9, then that means worst case scenario, time complexity, is n. Best case time complexity, 1. We say the average time complexity, which is theta. So big O complexity is worst case. Best case is omega. and best, say, what is the average? Well, we don't divide it by 2. You know, I can kind of say, well, average is, I want to say, take the length divided by 2. That'd be the average, wouldn't it? Well, it may actually be the average, but we always say that what is the average time complexity? You know, it may be 4.5, but you know what? I'm going to plan for the worst. I don't know what it's going to be. I'll just expect the worst. It's 9, or it's n. So best case time complexity on this, on a linear search, I find it right here. Worst case is here. Now, are these sorted? No. No, they're not sorted. On this one, if I wanted to find the largest value, I'll go through it pretty much the same way, but this, what I'm looking for, essentially what I'm going to do is when I read this first one, I'm going to say that's the biggest one, because that's the biggest one I found at this point. Let me compare it to this one. Now which one's the biggest one? All right, this one's bigger. Now this has become the largest. Let me compare this. No, no change. Oh, make it 70. Make it 80. No change. No change. Make it 90. No change. How many times did I have to go through it? 9 times. 9 times to find the largest. How many times would I have to go through it to find the smallest? Unsorted. 9 times. Let's say that this were sorted. How many times do I have to go through this to find the largest one? 1. Because if it's sorted, I know the largest one, if it's sorted ascending, the largest one's here at the end. If it's sorted ascending, the smallest one's over here. Okay. So different operations on here will take different amounts of time complexity. If this was sorted, it only takes me 1 because I can go right to the end. Or I can go right to the beginning to find the min or the max. If I want to find the average, man, I've got to go add up each one and then divide by the length. That's the average value. What is the median? Well, I can calculate that. And these are all mathematical, statistical terms. Median is the one right in the middle. The mean is the average. The mode is the one that's in there the most frequent number of times. That's assuming that things can be in there more than once. So there's a lot of mathematical assumptions that take place in here. I think this is about the extent of the math that we're going to deal with in this. It's looking at averages and things like that. So on a linear search, this is a one-dimensional array. The arrays are of a length n. This one happens to have n equal to 9. We've got a step-by-step how to search this algorithm. And it'll go find, it outputs the value of the index as we go through it. Okay. We've got code down here that's available to us, whatever language we're dealing with, on what a linear search is. We've got our driver code say this is the main, we'll go ahead and run it. We have a given array, 5 values. Let's go find x. We invoke or call the len array, which will tell us how long is this array. That gives us the value of n. And that doesn't change as we go through this. If that array was changing, that would be a little n. So for this, we'll call our search function. It's a linear search function. It needs 3 values. What we're looking for, which is x, the length of the array, and the array. So we pass it 3 values. And it's going to return a value. And that value is either going to be the index or -1. -1 if whatever we're looking for is not there. And if what we're looking for is there, then return that value. So here's where we define in Python our search array. The 3 arguments that we already talked about. And for I, each item in the range 0 to n. We're going to start at the first index and we're going until the end. If array I is equivalent to x, return I. Go to the next one. Go to the next one. Go to the next one. This assumes that x only exists one time. Because this function returns one value. And when we return, that function's done. Okay? So that's a linear search. Now, a linear sort, what kind of sort are we going to look at? Now, these are all sorts of different types. We can do a selection sort, a quick sort, bubble sort. Let's look at a bubble sort. I say, man, why don't I just use that built-in sort function? What kind of function, what kind of sort is it? Is it as efficient as the bubble sort? We say, well, how does a bubble sort work? Well, we input an algorithm, or I should say an array. So there's 5 values in it. And we compare the first one with the second one. And if the first one's bigger than the second one, we're going ascending. If the first one's bigger than the second one, we swap it. And then we go to the next. And if that's larger, we swap it. So we go through the entire array and find out if that first value is larger than the next one. And we walk it all the way back as far as it needs to go. And when we're done with this first iteration of walking through this array, we know that the first value is as far back as it needs to go, so that at the end of this first iteration, I know that the last item, at a minimum, the last item in this array is sorted in ascending order. And then we go through it again. And the second time we compare. And here's what we got. Compare 1 with 4. Is 1 bigger than 4? No. Is 4 bigger than 2? Yes. Swap. Is 4 bigger than 5? No. Well, we're pretty much done because we know 5's what we did before. And we'll go on through it again, each pass, we go through to make sure this thing is sorted. All right. Technically, how many times do we go through? N times. Each time that we go through the array, how many operations did we have? N operations. So the time complexity on this thing, and here's the code for it, it's a bubble sort. We can do bubble sort ascending or bubble sort descending. And when we look at time complexity, n squared. That's n squared because we go through this section of the loop n times. And we go through this section of the loop n times. N times n, n squared. So that's worst case scenario. This thing's totally unsorted. It's going to take us n squared times to go through it. If there were 5 items in this array, worst case scenario, we're going to have to perform 25 operations. Best case scenario, we'd only have to do 1. But we really can't do just 1. Can we? And know that, yeah, it's sorted? We would have to go through n squared to ensure that it was sorted. So, worst case scenario, n squared. Big O, n squared. Average time complexity, which is theta. It looks like an O with a horizontal squiggly line through it, or a line with a dot on it. Theta, we would say, is n squared as well. So on here we say the time complexity is n squared. I'm not dealing with space complexity of this, but they give it to us. They say space complexity is, for big O, worst case scenario, it's constant. It's 1. Now, with that said, and what that means is we don't grow in space over time. However much space has been allocated at the start, that's how much space we'll use. We're not generating or creating more, taking up more space along the way. So if I wanted to compare that algorithm, the bubble sort, with, let's say, a selection sort, going smallest to largest. Now, a selection sort, I'm not going to dig into the nuances of it, but the time complexity of selection sort is n squared. Well, time complexity is n squared for this one, and bubble sort was the same. Why would I choose this over the other one? Well, auxiliary space. So the space complexity, it's the same. So these are essentially the same, but the only way we would know they're the same is if we went and did the analysis of them. So it wouldn't matter in time and space complexity if I was using a selection sort or a bubble sort. And that's where this is all going, is the ability to know, if I do this, how ugly is it going to get as far as the processing of it? Is this efficient or not? Now, one of the things that is discussed in the text, I can't remember if it was in the first or second chapter or if it's in this one. It's in this one, and here it is. So we've got some code here, and this is setting a benchmark. We're going to have a problem, and we're going to use a tool. Now this tool does take time to evaluate, but it's not significant to impact the efficiency of the algorithm. So if I'm measuring the time it takes to do it with this time function, and I'm applying this time function to the selection sort, and I'm applying this time function to a bubble sort, we're comparing apples and apples as far as how we're going about measuring the time it takes to do it. So essentially, what happens when we use this time function or import the time library? In time is the ability to go capture right now, this millisecond in time. And we find out what time is it right now at the start of the loop, and then we find out what time it is here, and so subtract the start from it, and that's how long it took to perform that for loop. All right, from here to here. Now, we keep going through this thing time and time again, and it's incrementing as we go. But we print elapsed each time. Print it each time. Print it each time. And this will allow us to keep track of how much time it takes to do each iteration. This will tell us how much time it takes to do the entire function. So essentially, we could do this using that time function in our bubble sort algorithm or in our selection sort algorithm to see, are they really the same? And they are the same on the same processor. But if I was using two different systems and measuring one on one system and the other on the other system, the processors were not the same. No, they're not going to take up the same amount of time. Okay. So we can go through and measure it, and the problem will go through and say, well, how big is the problem? And on this one, what was it, 10 million? Goes through, it's 3.8 seconds. Double it. Double the size of the problem. Go back again. Double it, go back again. Double it, go back again. So we know how long it takes in seconds to do however many iterations through that loop. If I wanted to know how long did it take to do the whole thing, I could have checked at the start and checked at the end. They're looking to see how long does it take to go through just an iteration of the for loop. So we have tools available to us to perform tasks. We have an array class that allows us to have sequential memory. It makes it a little more efficient than using pointers. We've got the time function that we can use to actually measure time and see how long does it take to do something. One of the things that we're going to deal with later on, I'm not going to deal with it so much now, and they talk about it in this example, is recursion. And recursive functions call themselves, they talk about it, they don't actually do it, but they talk about it here. We'll deal with recursion and recursive functions more in trees. I'm not going to deal with it so much in sequential. Depending on the algorithms we're dealing with. There are some algorithms, sort algorithms, that are recursive. When we get into recursion, we're going to take that slow because that can be confusing at times. I'm not going to dig into the memory aspect at this point relative to space complexity. We're dealing with time complexity. Okay. So we deal with time complexity. Here's two examples of time complexity. One, this one right here where it says n, that is linear time complexity. Essentially what that means is, it says problem size is our x-axis, operations is our y-axis. If my array is n equals problem size, and the problem size is 10, an array of 10 length has 10 operations. 20 operations. 30 operations. So that's a linear diagonal line. As far as you go this way is as far as you go up. So the next one is like an example that we had before, where we had the bubble sort. The bubble sort was n squared time complexity. For problem size, you square it to get the number of operations. So if the problem is 5 in length, it's 25 high. 10 in length, it's 100 high in the y-axis. That grows really fast. Or we'll say it gets ugly really fast. And if the problem size, or n, is really, really, really big, then it's getting very, very high when it comes to the number of operations that are taking place. And we see it grow here. Problem size is 10, or 1,000. Well, if we're linear, operations is 1,000. But if we're dealing with n squared, that bubble sort algorithm, that's 1,000,000 operations. Okay. So the order of complexity is, as we go up, the larger that value of the function, the larger time complexity, the more operations it's taking. Now, let's say that it's constant. It's constant. This function, there is no n. It's always 1. Look, that's a line, horizontal line at 1. Doesn't change. It's not bad. We start at 0 with everything we're doing here, so we're not really going to see something down at 0 that runs across. So the functions we're dealing with n is always greater than 0. I could have a line up here, but for what we're doing, we could have linear, exponential, could have n factorial. What if we had n cubed? Yeah, that's uglier than n squared. N to the n. Man, that's really ugly. That's 1,000 to the 1,000th power. And if we were talking about really, really big data set, that'd be 5 trillion to the 5 trillionth power. That's a really, really big number when it comes to the number of operations taking place. So the order of complexity is how it grows. There's a sequence here. Logarithmic would be smaller than n. And I've got a, let's see, I've got a chart that I can show you. Let me pull it over. There's a chart real quick. Big O time complexity. So there's log of n, and we've also got big O of 1, that's constant time. Above it is log of n. Above that is n. That's what we had, and it doesn't look like it's as big a number as we had before, big an increase as we had before. But we're looking at all these together, and it takes a lot to get them all in the same thing. So we're going to say O to the n log n. It's a logarithm with the value multiplied to it. I'm not going to get into how we do that mathematically. That's something that we would deal with in a math course. I may point you in the direction of some resources that can help you, but I'm not dealing with that right now. N squared, we saw that one before. 2 to the n is worse, and then we get n factorial, and even beyond that would be n to the n, is when it's really, really ugly. Worst case scenario is what we're talking about with big O. Okay, so as we move forward, and we talk about big O notation and how things work, the role of constant of proportionality, we're dealing with coefficients that are usually ignored during big O analysis. So when I say plus 1, let's say I have a formula that says plus 1. I'm ignoring that plus 1. Because in the whole scheme of things, it's insignificant. I'm not going to dig super deep into that. I want to focus more on searching for the minimum. Now they're saying, now let's do this with a list and search for the minimum. And in this, the assumption is this thing's not ordered. And I talked about that. We have to go through every item in there. It's going to take us n iterations, n number of tasks to find out what's going on. What is the minimum? If it's a sequential search of a list, well, we dealt with that before. Till I get to the end, if the target is what I'm looking for, Okay, I'm going item by item. Worst case scenario, time complexity, n. Best case scenario, 1. Average, or theta, that is also going to be treated as worst case scenario, so that's going to be n. Okay. So when we talk about best case, worst case, average case, yeah, average case is divided by 2, but I can figure out what the average is, but when asked, what is the average? What is theta? Theta is, when we're talking about big O notation, theta is whatever worst case scenario is. Always treat theta as worst case scenario if I ask you. So what's theta for this algorithm? Theta is going to be whatever worst case scenario is. So if worst case scenario is n squared, just tell me it's n squared. If worst case scenario is n, then tell me theta is n if I'm asking you what theta is. Okay. Now, in a binary search, if I'm looking for 10, we have what we see in front of us here in figure 3.7. An example of divide and conquer. And this is a very efficient search algorithm. All right. Now, what we saw before in the search algorithms we looked at, the selection search and or I should say the linear search and the bubble sort algorithm, or let me see. No, we looked at linear search before, and linear search start to finish, we went through it n times to find whatever we were looking for. So let's say I'm looking for, and this is a sorted algorithm, I'm looking for a value, and it could be a random number. So let's come up with, well, let's look at this example first. This array is 9 items long. And the divide and conquer essentially means, let's go to the middle. And if the length is an odd number, then we're going to the lower side. And on this example, essentially we say 9 divided by 2 is 4.5. Let's look and compare values 4 and 5. Look in index 4 and index 5. Now, one of the things that we assume to be able to do this divide and conquer is that this is already sorted. It's in ascending order. It could be in descending order. It doesn't matter. I would just change how I compare things. But for this, I'm looking for the number 10. And I don't know where it is. But I come in and, you know what, I'm going to go look for it. And I'm going to do a comparison here. And I look in number 4, and I look at number 5, and I say, is number 5 greater than 10? If it is, I need to start looking over in number 4. And I say, is number 4 less than 10? And if it's not, well, I need to come look over here. If it is, I know there's no 10 in here. Okay, so I'm trying to find out, is 10 in this half? Or is 10 in this half? And when I find out that 10 is in this half, that's all I want to look at is just this half now. So I did essentially an operation to find out, is it on this side or that side? I did a single comparison. And I found out I'm either going this way or that way. I do the same thing over here. Divide it in half and do a comparison. Is it here or there? Is it here or there? And as I go down, it's going to end up, I'll find it in worst case scenario. How many? 1, 2, 3, 4 iterations. If this thing is 9 items long. 9 items long, it only takes me 4. If it was 1,000,000 items long, it's going to take me at most 20 comparisons. As opposed to if I was going linear, looking for number 10, I got to go through every doggone one if it's not sorted. If it is sorted, I don't know where it starts. I don't know what the number is, and it really doesn't matter what the number is. I search any number in an array of 1,000,000 items, I can find it in only 20 comparisons because I use that divide and conquer. So we can measure this and know, man, that's really efficient. Okay? And worst case scenario is big O log 2 of n. That's the time complexity for the divide and conquer search algorithm. Other search algorithms? Is it that low? Well, we know linear. Linear was n. Man, that's not where we're at now. We're better than that. Because when we looked at here, that's somewhere in here. No, it's somewhere down here. Is divide and conquer. Here is sequential. So we just shaved that way down by using divide and conquer instead of linear. So that's the kind of things we need to look at. We've got a lot of object-oriented programming that we're dealing with here. All right. And everything that I want to do with this is object-oriented. And we're going to create an instance of an array n long. That's an object. And we have functionality associated with it. All right. By default, it has the init function. It's a built-in function. And it is, and this is an example of object-oriented programming. The init function is our constructor. I'll talk about that here in a little bit. Jump into something that's here we're looking at a basic swap function. Now, if you had me in C++, C#, or in COP3530 Intro to Programming, we dealt with a swap using a temp variable as a placeholder. So here's a swap function, and we got two ways to do it. I'm going to ignore the red to start with and do it. We create this temporary variable. I get what's in the first position. We say we start out with I is 0. Get what's in the first index, store it in temp. Okay, I get what's in the second one, put it in the first one, and then I get what's in temp and I put it in the second one. Work my way right on down through, or this is a simple swap using a temporary placeholder. There's another way that we could do it in Python, and I could say list I, comma, list j equals list j, comma, list I. So get what's in j, stored in I. Get what's in I, stored in j. Happens just like that. So I pass it the list, pass it the indexes, do the swap, or the values of the indexes that we're dealing with. Do a swap for me. And that's a simple swap. We have to have swaps to do a sort. And I showed you the sort and how we do the swaps. Here, this walks through the selection sort that we talked about already. And this selection sort, we talked about the time complexity of it, and here we are going through it. And what was the complexity? Time complexity of selection sort is n squared. What was the time complexity of bubble sort? N squared. Okay. So we're able to go through for each level of the loop. So here's a loop, outer. Here's a loop, inner. N for each one. What's the total? N squared. So this is a bubble sort example. We talked about that earlier. Insertion sort, another one. Let's go look at insertion sort. I've got it right here. We'll open it up. Go into Geeks for Geeks. I can scroll down. This walks you through it, what the insertion sort is. Gives you pseudocode for it. Non-language specific. Here's whatever code you want, whether it's C++, C Sharp, or C++, C, C Sharp, Python, Java. What's the time complexity? It's the same, n squared. So it looks like any of these sorts are nested loops. We've got a for and we've got a while. On this one, we've got a for and a for. Inner and outer loops, each using n time, we're going to end up with n squared time. The difference between them, then we're going to look at space complexity. If time complexity is the same, good. Let's go look at space then. And if I have a ton of RAM, it's not a big deal unless I'm dealing with really, really big values for n. So we talk about different ways of sorting, which one's faster, comparing the different ones. Okay, here's a table, and we're looking at time complexity of n squared, n log n, and n. N is linear. Here's a log function. So we see that linear time is pretty doggone fast. There's not a lot of operations taking place. But as we grow, and we're up here in n squared, man, that's a lot of operations. So this was n equaled 32,768. N equaled 32,768. When we're talking about n squared, man, that number got really big. So we've got a quick sort this allows us to partition the array and sort in segments. We've also got a merge sort. I'm not going to dig deep into these different types of sorts. Okay. The merge sort, in a roundabout way, breaks things down into divide and conquer as well. Now, there's an example. One of the exercises deals with Fibonacci. And I walk through that. I'm not going to deal so much with recursive algorithms. Fibonacci's a tree. We deal with recursion in tree collections, hierarchical collections. And we'll deal with that in a later module. We'll be efficient about our time. We've got a linear algorithm, but it's not, it doesn't look linear when we're doing it, okay? So, Module 3 is not so bad. There's a lot of things we need to take into consideration because there's a lot of new stuff. We're dealing with programming, but we're also looking at algorithms which are in mathematician speak. Mathematicians start at 1, programmers start at 0. It'll get a little confusing there from time to time. All right, take your time and go through the algorithm or through the exercises, and I'll see you in the next module.